modern natural language processing. So just a poll, how many people here are like understand natural language? Like have done natural language processing before, understand it, or like have some experience with it? Cool. How many people here like understand neural networks and like deep learning in general? Okay, good. So this talk is like kind of an in-between. It's like for people who have a little bit of like deep learning neural network experience, but haven't necessarily been exposed to like natural language processing and some data optimizers there. Hopefully this will help do some of those, help like explain some of that stuff. Cool. So the problem with NLP, which I faced recently, was that when I was making these slides, it was about XLNet, one of the top models in natural language processing. And this was, I guess you can't see it clearly, but this was like this was from a search on XLNet, which I did last night. And last night, there were 2 papers that were released in the past 2 days that beat XLNet. And so I tried to include it in my talk, but like this is a very, very active area of research where like the state-of-the-art models are being beaten like on almost an hourly basis. That's like 10 hours ago. So this talk is going to be divided into 3 parts. The foundations, which are just basically natural language processing, what we're trying to solve, what are the kind of problems we're trying to work with, the deep learning frameworks that you need to understand some of the state-of-the-art models, and then the actual state-of-the-art models. So in foundations, we'll start by actually explaining what natural language processing is. So language is potentially one of the most important technologies we've developed as a species. While there are many animals out there that can see, humans are unique in our ability to communicate with each other through like a complex and subtle tool like language. It underlies most of our systems and most human systems that exist. So if we want to build computers that interface with human systems effectively, we're going to have to understand language in some way. And this talk is about some of those models which try and do that. So what are the kind of problems then that we care about? Because understanding language is a very general kind of idea. What can we actually concretely say we want to do? Maybe the most general and easy task to think about is the Turing test. This is like the goal of all natural language processing systems. Essentially, it's a computer that can generate language, that generate interactions through language with a human questioner that are indistinguishable from interactions with another human. This is like kind of like this is the holy grail of natural language processing. However, this is kind of a problem because you can't backprop through human interface, so we have to break down the problems into things that are more easy to solve. So we actually break this down into 3 other types of tasks, which are easier to solve and are kind of tasks that we can actually optimize on. There are single sentence tasks, and these are things like telling what the sentiment of a sentence is. They're like telling whether a sentence is grammatically correct. 2 big models here, there are 2 big data sets used here are Blue and IMDb. There are similarity and paraphrase tasks, and these are taking 2 sentences and saying whether they're similar in any way. And then there are inference tasks, and these are more like question-answer tasks, which you try and infer whether the first sentence implies the second, contradicts the second, or like is not related to the second. And these are kind of tasks, and these are the data sets that we'll be using to evaluate the models. Some of the applications, I'm sure you're all aware of the natural language processing space, like all of the cool tools that are out there. Text classifiers for spam, sentiment language, language models that generate like summaries, headlines, machine translation, knowledge-based integration, chatbots, and personal assistants. There are plenty more. These are just like, this is a non-exhaustive list. So the first techniques that we came up with when we were trying to solve some of these problems were hand-engineered features with like traditional statistical models. We separated the space into 2 features that the models use to predict, to solve the problems, and the actual models themselves. Classically, we use some of these techniques, and And like they were state of the art until very recently. So, and we used a lot of the intuitions we gained from these techniques in current models too. So now to the second part, so the actual deep learning kind of stuff and why it's useful. So one question that might come up is why do we need to use deep learning? Why not just like continue with the traditional statistical models? The problem is the curse of dimensionality. If you have a large vocab, the size of your models scale exponentially with the size of your vocabulary, which means that as your vocabulary gets bigger, you need much more compute, and that's not feasible. So we use deep learning as a way of like compressing that dimension. Yeah. So the way we do that is we take advantage of this hypothesis that every word can be understood by the words around it, and using this idea underlies almost all the techniques that are used in natural language processing. So some of the first techniques that were used were word embeddings, and the idea behind this was to use the word to predict the words around it, and that's called the skip-gram model. And the other one is to use the words around the word to predict the word itself, and that's called the continuous bag of words model. So these are like the two models that like started the whole deep learning in machine learning. Deep learning in NLP space, and they got a lot of popularity, more so because of their ability to have these distributed representations that were quite semantic. So like these groups here are very similar, despite having different words. So there was an idea that you had this kind of representation of language that was semantic and could be like manipulated using math or like algebra, which was very interesting. However, there are some problems with some of these distributed representations. For instance, idioms are really difficult to capture because things like hot potato and Boston Globe are different. Like they don't represent like the mean of the two embedding vectors for each of the words, as well as their good and bad and other words share similar context. So they may actually end up having very similar distributional representations or embeddings, even though they're considerably different. There's also polysemy, which is a problem. So like a river bank or a money bank, how do you tell the difference between the two? So these are some of the problems that are faced. In addition, there's a question of like whether these embedding vectors actually capture meaning in the actual sentence or in the actual text. A good example of this is the Thai library experiment. If you're in a library that's full of Thai books and you don't know Thai, can you actually learn anything from there? Just like even if you have infinite time to compute, like it's unclear whether you can or cannot. And then there's out of vocabulary words. So if your word doesn't appear in your vocabulary, you don't have an embedding for it. There are techniques to overcome this, like fast text and sentence piece, and these break down the words into component chunks. Sentence piece is like the thing that's used in most of the state-of-the-art models that we'll talk about. So once you have these embeddings, what can you actually do with them? Benjo et al. Had the intuition that you could actually use these embeddings and just pass them to a dense layer and have that like be used as a classifier, and that was like what was used initially, and they found like good results there. However, it was in around 2015. There was a blog post by Andre Karpathy which showed that if you use recurrent networks, you could actually get much better performance on these problems. So you could actually use this. You could unroll this dense network and have this recurrent network that would have context information as it moved through the sentence, and it was like it like mimicked how humans read, and that's what you could actually get really good results there. Here's an example of like the kind of sentences that like just using recurrent neural network can do, another recurrent neural network it can create. This is the recurrent neural network trained on Shakespeare text, so this is already really good. it could create, like, this is gibberish papers that were created in like perfectly good syntax, so surprisingly accurate for like a model that only like predicts a character at a time. And there is one problem with this though, in that when you roll out this recurrent neural network, the weights from here have to go all the way down here and to update here. So that is a vanishing gradient problem, and that causes a lot of issues if you're looking at long chunks of text. So as a result, there was another innovation that was used, which is the gated RNNs, and there are two types that are particularly famous: the LSTM and the GRU. Those essentially have gated connections that allow the network to pass information over long boundaries. Another very important innovation that came up was the bidirectional recurrent neural networks that not only went from start to end, but from end to start again, and combined the vectors to create like better representation. So now you not only have left context, but also right context before you could use. So that was useful for predictions. So the way you could use some of these, the way that some of these recurrent neural networks can be used is like in sequence models. So in this model, you have an encoder network where the hidden weights are passed to the decoder, which then decodes the French sentence into English. So then here you have two neural networks. One is the encoder network and one is the decoder recurrent neural network, and they communicate through the hidden weights to do machine translation. And this was like a really powerful model, and was like and showed like the applicability of deep learning to machine translation. However, there was a problem here in that if the first word was required, if the information from the first word was required for the output of the last word, the information needed to travel all the way from like the first recurrent network all the way to the last recurrent network, and that might not be possible. So in 2014, there was an idea. The idea of attention was created, which was essentially using another neural network so that the decoder network could look back at the hidden states of the encoder networks to identify what was important to like do the translation. So this was a really big model. This was a really big breakthrough because this was like when this was when the deep learning models were actually surpassing some of the classical models, and this is like what they use in Google Translate. This was like one of the models that they used in Google Translate. Taking this a step even further, in 2017, there was another paper by Oswani et al. that completely got rid of the recurrent neural network idea and only used attention. So the idea was you would have a set of sentences as input, and all the sentences would be, and the way that this model would work is that the set of words that came as input would pass through this attention layer, the self-attention layer, and would keep going up so that there wasn't any, so a recurrent neural network would actually go through each word separately, but the transformer network, this is called a transformer network, would basically take all the words in together and do the analysis on it like at the same time. So this is actually a really important model because this is like the model that's used by all of the modern state-of-the-art models. So that's basically what gets passed through the layers of the network, and you also have positional encoding here that tells you where the word is in the list in sequence, because in the recurrent neural network you actually pass through the words in order, but here you actually don't know the order unless you have a positional encoding. So these transformer networks have multiple different connections or multiple different self-attention modules where each word attends to different words in its own sentence, and that's what gets passed to the dense layer, a combination of the attended words, or like some nonlinear combination of the attended words. So, so I just want to stop here for a little bit because it's actually a relatively complex model. Does everyone understand this? If you have any questions, please ask. I'll be happy to explain here.
So there were two encoders.
Yeah.
So both the encoders takes all the words in the sentence.
Yeah.
Then find this.
Yeah. So the way that it works is each self-attention module here looks at the full sentence, and it outputs like basically a combination of the attended words, and then it passes that to a feed-forward network. But then on the output, what happens is you take the hidden vectors from here and you pass those into the decoders, and that goes through. And at each step, the decoder uses those hidden weights to produce the next word. So essentially, in the encoding RNN, you go through each step sequentially, but here you look at the entire input sentence at the same time, and at the output sentence, you basically just like go word by word, and you use the hidden weights from the encoder to identify what to output next. Any other questions on this?
Does the self-attention piece, does that deal with like grammar, the modifiers?
Exactly, so that's like kind of the idea behind it. The idea is that it should understand what to attend to. So for instance, if you're a pronoun in the sentence, like if you're a sentence, the animal, and the animal crosses the street and it is tired, it would attend to both animal and street, but it has to identify, it has to learn basically what the pronoun needs to attend to and what's important. So it has to learn the grammar. This is like a very general model, and after a lot of training, it actually gets a really good job of like figuring out the grammatical structure.
So how should I interpret this diagram? What does a bold line mean between two words here?
This, yeah. So the way that this works is each word on the left side is the word from the. So both sentences are the same, but like the word. So in this example, if you're looking at like, let me find the example. But like, yeah. So we can just look at law, right? So if you look at the word law, the words that are important to understand the word law are the, law, and its. So its actually needs to have the information from the word law or from the encoding of the word law to like continue processing.
What's it mean for a word to attend primarily to itself? And with should it make sense, I get that. But like application,
So if a word is attending to itself, it means that it so it's technically every word is attending to every other word.
No, I understand. But like if a word attends primarily or has the highest weight to itself.
Usually that means it's like a subject. Usually it means that like it only really matters. That word only really cares about itself. It doesn't really matter what the other words are. So if you just have like a sentence where there's nothing modified, or like if the word itself is just a subject and object, you don't really. Yeah. I mean, someone else might need to attend to it, but like if nobody else is attending to it and it's not attending to anybody else, and it's like pretty independent, you could switch it out for any other word. Then like that's probably what it means.
So then in prediction time, so at training time, it's essentially bidirectional, right?
It's not really bidirectional.
And then
It just has everything. Yeah.
But then in prediction time, it's only one way, right?
In prediction time, it does the same thing. Like in prediction time, it's like the output of this is it takes the full sentence as input, and the output is just a hidden state. It's a hidden state.
Okay.
And the hidden state like goes into this decoder module, which is like completely different.
So it outputs an entire vector in your time.
Yeah, exactly.
Okay. So like I primarily work with time series. So if you were to translate this to the time series space, you'd be primarily outputting the next sequence, essentially.
You're outputting what you essentially output from here.
But the decoder would output.
Yes, exactly. The decoder would output the hidden state. Cool. If there are no more questions, this is like probably the most important module that was like built because all of the modern techniques that have like stereo performance and were able to beat human baselines are built on the attention on this transformer network. The last part, which is important, is the idea of a language model. So a language model takes in context, so everything to the left of a word, and uses that to predict the next word. And the idea of training a model on this was, so we have all these tasks. Each task seems to be kind of independent of the other one. So what is one general task we can use to solve all, that can be then translated to solve all the other tasks? And it turned out that in 2017, there was this paper on the unsupervised sentiment neuron by OpenAI, where they trained a language model, and they found that one of the neurons in the language model gave a really strong signal for sentiment, and that gives some indication that training a language model could generalize to other tasks. And that insight is what led to all of the models. You actually build some of these models. Now we can talk about some of the actual watershed models that have been beating these benchmarks. So the first wave of these models were Elmo, ULM Fit, and OpenAI Transformer. All these models basically were language models that, when trained, they were able to beat human-based, not human-based, sorry, they were able to beat all the classical baselines, and this is what the current models are based on. So Elmo basically uses the bidirectional LSTM, the hidden states of the bidirectional LSTM, trained on a language model task, and uses that to do predictions, and it does a really good job. This was the first paper to beat multiple sort of baselines in one paper, and using just one model. The second paper was ULM Fit by Howard et al., where they basically came up with a bunch of new ways of fine-tuning these language models to be used for different tasks, and they were able to also beat many classical baselines using this new technique. The next model was the OpenAI Transformer, or GPT. This took the transformer architecture that we saw before and uses that to do predictions on the next word. So it uses transformer architecture, gets rid of that whole decoder part of it, and uses just the encoder to predict the next step. And that's what this GPT model did. This beat a lot of baselines and on multiple tasks. So the other two were primarily classification tasks, but using different types of, by changing the input to the transformer module, you could actually get a lot of different tasks. You could do classification, obviously, but also entailment, similarity, and multiple choice, and get state-of-the-art results on all of them. So yeah, this is an example of the output. They beat state-of-the-art methods on almost all the tasks that you can see here. So this did take 1 month to train on 8 GPUs. So at this point, it starts to become pretty infeasible to train these models independently if you're not working at a huge organization. Though they do release these models with a weight, so you can fine-tune them for your own tasks. Once the first wave passed, there was a huge excitement in this area, and there are at least 5 models that were able to beat human baselines and actually get better results than we had ever seen before. And these are BERT, GPT-2, XLNet, Roberta, and Ernie-2. These two came out this came out the day before this thing, this came out yesterday.
It's a short first wave.
Well, it's 1 year, but people have moved on from there already. So the idea behind BERT was, in OpenAI GPT, you train this language model. The problem with this language model is that in a language model, you can only look 1 step ahead. You're predicting 1 step ahead, so you can't look ahead. So a way of describing this is, if you're going to look at the sentence, New York is a city, if you go to New York is, and you're predicting A, you can't look at the word city and you can't look at the word A, because that will give you information. But if you remember, the transformer network looks at the whole input together. So in the GPT model, you mask out the left context, the right context, as well as the word itself, and you only use the left context. And that means that you miss out on the information that's really important. And that's what BERT tries to use both of the right and left context to do predictions. So in BERT, they essentially take the sentence and they mask out this. They randomly mask 15% of the tokens. Once 15% are masked, they try and predict the masked tokens. So if you remember skipgrams, this is basically the skipgram problem, but they use a huge transformer network to do this instead. And this is what, and basically this is the model that has gotten state of the art so far. Again, this is like similar to GPT. You can change this model to for different tasks. So the same for different tasks, you can use different inputs and output pairs or combinations and get different results. This beat state-of-the-art on almost all problems. It was also able to be state-of-the-art on they were also able to beat like human baselines, though this model is good. The human baseline, the fact that it's human baseline is not that significant because when you actually look at the outputs of these models, they don't seem to be as good as the numbers suggest. So that gives us some indication that maybe it's the problem with the data sets, and not actually the and not the fact that the model is beating humans. This took the BERT model took 16 cloud TPUs, so 64 TPU chips that took 4 days to complete. This is like already in order of like over $100,000 to train each model. So very, very far away. They have released 2 models, BERT large and BERT base, and those you can fine tune for your own tasks. But again, these are like huge training jobs that have a lot of engineering effort gone into them. The next part is XLNet. Honestly, XLNet is very similar to BERT. It just like extends BERT a little bit more. The problem, it tries to fix the problems with BERT. One of the problems with BERT was the masked tokens. In reality, you don't actually see masked tokens in a sentence. Like if you're doing a task by classification, 15% of the words are not dropped out of that sentence. So it's unrealistic to drop it out and then try and train a model and then fine tune a model without the dropped out words. The BERT generates predictions independently, so the idea of BERT does something that sort of, you have a sentence, New York is a city. BERT will, if New and York are masked, then it tries to predict New from is a city and York from is a city, but it doesn't have context of New when it's predicting this or York when it's predicting this. So XLNet actually does have access to that. The one positive of BERT is that it uses bidirectional context unlike GPT, so we want to try and keep that there. So XLNet tries to combine the bidirectional context as well as make these a little bit better. So the way they do this is using random permutation. So a classic language model will take something like this as input, and so it'll take like these words and predict the left context and predict the right context, but the problem with that is you don't have access to the right context. So the way you can fix that is by randomly permuting the order in which you look at the words and then use that order to predict the next word in the randomly permuted index. And that way you can actually, using random permutations, you get access to both the left and the right context, which is important, which is like what we found, which is why BERT did better in GPT. So a BERT model would do something like this. It would mask out a token, and it would try to predict that token from the masked tokens, while XLNet randomly permutes the way it looks at the tokens without masking it out, and the random permutations serve as a way to get both the left and right context of the sentence. Another innovation of BERT was to use two-stream. So to actually get this to work, you have to use something called two-stream self-attention. So instead of just using the regular self-attention that we saw in the transformer networks, you need to have access to both the word that you're trying to predict, and the word, and all the words before that, and that's not possible in a randomly permuted order unless you have two streams of input. This is a little bit technical, but I'm happy to talk about this a little bit more if people want to. But essentially, this is a trick that you need to use to allow the permuted order to work in this context.
Could you talk about it a little bit more?
Yeah,
I
sure.
think it's probably a pretty technical crowd.
Yeah. So the idea is, the way that this works is you have a bunch of inputs. So each of the elements on the left here is an embedding for a word, while the elements on the right are random vectors. And the idea is there's two streams, the H stream and the query stream and the context stream. And in the context stream, you have access to the words directly. So you have access directly to these words, and these words are what you're. So these words essentially are the ones that propagate up and train these H modules. But you can't use these words to then predict the next word because the next word is used in that context. So instead, you have another stream which can only look at the previous the previous vectors of the context stream. So the way this works is, for instance, if you're predicting New York is a city, you have like New York is. So and if you're trying to predict is, the is word is actually available to the context stream, and that's used to train the context stream network. But when you're doing the language model only has access to the context stream that was trained on New York, essentially. So
do you update the weights based on both? Or there's separate weights for both streams?
they're separate weights. They're two models that work simultaneously with each other.
Yeah.
One which works for one which updates based on
The context stream.
the current word that you're looking at as well, and the other one that updates, and the other one that only uses the previous words to so you need the context, but you can only access context before a certain point. But while in the context stream, you want to have access to that word for the next word.
So streams basically just means two models.
Yeah, it's two attention models basically. It's two attention
And one
models.
has access to things at certain times, and the other one doesn't.
Yeah, exactly.
And one that has access to certain things always gives the weights to the other.
Yeah, exactly. So the context stream is what has access directly to the weights,
Yeah.
but or the embeddings. But the query stream only has access to to those weights through the context stream.
So it's like, the classical idea of training embeddings in your classifier at the same time? Or like in different layers? Like you train your embeddings as one output, you train your classifier as a separate one?
Yeah.
It's like if you took your embeddings and moved up to the same point you were training your classifier at, right?
Yeah. So the idea is you would use the outputs of these embeddings.
At the exact same step.
Yeah.
Like you update your gradient at the exact same step.
Yeah, exactly. It's the same.
So sorry to cut this off because I think some people are wanting to go home. So, I'm so sorry, I think this is great. You should just take it offline and then that's okay. Because we're over time.
So yeah, this is basically it, and the other thing that it uses is a transformer XL model, which rather than just doing so this is a classic transformer network, which just basically goes through a bunch of different streams and updates the weights for each stream, while transformer XL uses the weights from the previous segment to do predictions. So this actually has long-term memory. So XLNet actually is able to have much more long-term memory dependencies, which is why it's considerably better than BERT. Yeah, and they have this is an example of something that came out of XLNet, which is comparable to GP2 if you've seen that one. Again, they got state of the art on almost all the baselines, beating all BERT, UM, fit, everything we've seen before, and also beating some human baselines. Yeah. This XLNet cost took $245,000 to train because it ran on 512 TPU chips for 2.5 days. So debatable how useful this, how a lot of these models that came out recently have been, it's been debatable how useful they are because they're, or how different they are because they just have access to different amounts of data and different amounts of compute. So XLNet also had access to different types of data than BERT did, so we don't know whether it did better than BERT because the model was better or because it had access to different data or more data. So that's an open question. And yeah, that's an open question, and one of the recent models that came out there was Roberta, and Roberta showed that if you tune the parameters of BERT, you can get even better results than XLNet. So yeah, so arguable which one is like the best. There's still a lot of war that's like going on. We'll see what comes out on top. But yeah, that's basically it. That's everything I have. If you have any like specific questions, I'm happy to chat about them later.